RMO 2024. Problem 4. We are given 4 real numbers A1, A2, A3, A4 satisfying the constraint A1 squared plus A2 squared plus A3 squared plus A4 squared equals 1. Geometrically this means the point A1, A2, A3, A4 lies on the unit sphere in 4-dimensional space. These numbers can be positive, negative, or 0. The only restriction is that their squares sum to 1. Let's see a few examples to build intuition. Now let's understand exactly what we need to prove. We must show that among the 6 pairs of numbers A1, A2, A1, A3, A1, A4, A2, A3, A2, A4, A3, A4, at least one pair has squared difference at most 1/5. In other words, at least 2 of the 4 numbers are within 1/5 of each other. This is a pigeonhole style result. The 4 numbers cannot all be far apart from one another simultaneously, given that their squares must sum to 1. Let's build geometric intuition. Place the 4 numbers on the real number line in sorted order. A1 is at most A2, A2 at most A3, A3 at most A4. The 4 points divide the number line into 3 gaps. The total span from A1 to A4 is at most 2. Because all 4 numbers have absolute value at most 1. If all 3 gaps were greater than 1/5, the total span would be greater than 3/5, which is greater than 1.3. But the constraint that their squares sum to 1 prevents them from spreading out too much. By the pigeonhole principle, at least one gap must be small enough. Before the proof, let's establish a key algebraic identity. The sum of squared differences over all pairs equals 4 times the sum of AI squared minus the square of the total sum. Since sum of squares equals 1, the right side is at most 4. The square of the sum is non-negative, so subtracting it only decreases. We will use this upper bound in the proof. Here is the complete problem statement. Let A1, A2, A3, A4 be real numbers such that A1 squared plus A2 squared plus A3 squared plus A4 squared equals 1. Show that there exist indices I and j with 1 less than or equal to I less than j less than or equal to 4, such that AI minus rj, all squared, is less than or equal to 1/5. Let's now prove both solutions. Solution 1. Step 1. Sort and define the minimum gap. Assume A1 at most A2 at most A3 at most A4 without loss of generality. Define M as the minimum of absolute value of AI minus rj over all pairs. Since the sequence is sorted, M is the smallest consecutive gap. For any pair I less than j, rj minus AI is at least j minus I times M. Step 2. Lower bound the total sum of squared differences. Since rj minus AI is at least j minus I times M for sorted numbers, each AI minus rj squared is at least j minus I squared times M squared. Summing over all pairs, the total is at least M squared times the sum of j minus I squared over all pairs. Gap 1 pairs, 3 pairs, each weight 1, total 3. Gap 2 pairs, 2 pairs, each weight 4, total 8. Gap 3 pair, 1 pair, weight 9, total 9. Grand total, 3 plus 8 plus 9 equals 20. So the sum of squared differences is at least 20 meters squared. Step 3. Upper bound the same sum using the given constraint. We use the algebraic identity. The sum of AI minus rj squared equals 4 times the sum of ai squared minus the square of the sum of ai. Since a1 squared plus a2 squared plus a3 squared plus a4 squared equals 1. The first term is 4 times 1 equals 4. The second term, the square of the sum, is always non-negative, so subtracting it only makes things smaller or equal. Therefore the sum of all squared differences is at most 4. Step 4. Conclude solution 1. Combining the lower and upper bounds. 20 meters squared is at most the sum of squared differences, which is at most 4. So 20 meters squared is at most 4. Dividing both sides by 20, m squared is at most 1 over 5. But m is the minimum of absolute value of ai minus aj over all pairs. So the minimum squared difference is m squared, which is at most 1 over 5. Therefore there exists some pair I, j with ai minus aj, all squared, at most 1 over 5. Proof of solution 1 complete. Solution 2, proof by contradiction. Assume all pairwise squared differences exceed 1 over 5. So every absolute pair difference exceeds 1 over square root 5. Label x as maximum, y as minimum, u and v as the other two. Since x minus y spans at least 3 gaps each exceeding 1 over square root 5. X minus y exceeds 3 over square root 5. Also u and v differ by more than 1 over square root 5. Step 6. The contradiction. Use the inequality. A squared plus b squared is at least a minus b squared over 2. Apply to x, y. X squared plus y squared exceeds 9 over 5 over 2 equals 9 over 10. Apply to u, v. U squared plus versus squared exceeds 1 over 5 over 2 equals 1 over 10. Adding, the total sum of squares exceeds 9 over 10 plus 1 over 10 equals 1. But the sum equals 1. Contradiction. So some pair must satisfy squared difference at most 1 over 5. QED. Here is the complete solution summary. We proved that when a1 squared plus a2 squared plus a3 squared plus a4 squared equals 1. Some pair has squared difference at most 1 over 5. Solution 1. Sort the numbers. The minimum gap m satisfies 20 meters squared at most the total sum of squared differences, which is at most 4. So m squared is at most 1 over 5. Solution 2. Assume all gaps exceed 1 over square root 5. Using a squared plus b squared at least a minus b squared over 2. The sum of squares exceeds 1. Contradiction. The bound 1 over 5 is sharp. Achieved by the equispaced example.